that, I'd like to introduce our first speaker, Bing Yu from MediaTek. Bing is an architect within the AI group at MediaTek. And before he comes out, I'd like to make just a small announcement. You probably heard about the Vision Product of the Year awards. Jeff announced those in yesterday's keynote. Every year we have the awards program. We have an independent panel of judges that evaluate product entries from member companies of the Alliance. This year, the award for Best AI Technology went to MediaTek. So I want to congratulate MediaTek and Bing. Thank you.
Thank you, Dino. Hi, my name is Bing Yu, and I'm a mobile architect for MediaTek's Computing and AI Technology Group. And I'm going to share with you today is MediaTek's approach for edge intelligence. And I'm going to introduce our product position first, and followed by our approach, which is P90, and followed by the little bit introduction of our accelerators feature and architecture, and followed by our toolchain, which is very important, called NeuroPilot and the platform-aware ML kit. And before I go into the product position, I just want to give some personal opinion, because it is much easier if you have a product line and you apply the AI technology to your product line, rather than develop your AI technology and try to get in a product position. So maybe I'm biased, I'm from MediaTek, because we have a great product positions. And for the future phone and optical disk drive, it's a legacy product, we're holding #1 position. And for digital TV, we're also holding #1 and dominant positions. And for the mobile computing segment and smartphone, we're #2 worldwide, and the Android tablet, we're #1. And for the voice-activated device in the network connectivity product line, we enjoy the highest growth in today's market, and both of them, we're holding #1 market positions. And all the devices around us are getting smarter. And we're deploying the AI autopilot to our automotive product line by applying AI technology to enhance our ADAS product line. And we're applying AI camera technology to our smartphone to make our user able to take a better picture and get a better user experience. And for the IoT product line, we're applying AI appliance that we actually, using AI technology, introduce many new use cases for the appliance product place. And also for digital TV, we're using AI technology to detect the scenery of the video and the picture, and apply different technique to enhance the picture quality. And for the AP router, we're applying the AI Proto, which we introduced the computing at the edge for the router market segment. And for the voice-activated device, that's we enjoy the highest growth rate. We also has the #1 market positions, is we apply AI voice to enhance the voice activation, voice detection capability to the voice-activated device. And as you know, the AI applications is only limited by your imaginations. With all this application, who knows what else is going to come tomorrow, right? So, and we cannot do this alone, and we work with our partner around the world. In North America, we work with Amazon, Cisco, and Google and Microsoft. And we also have a lot of partners from China, South Korea, and Japan as well. And we all experience that inference is moving to the edge. And it's all around us. And for the following reason, because many of the applications that just cannot tolerate the network latency. Or sometimes they're in certain part of the area, you don't have connectivities. And I think Peter's talk, if you've been there, he's talking about it just spend too much energy transferring the raw data to the cloud to do the inference. It's much more energy efficient if you just do the inference close to where the sensor data is collected. And users are demanding privacy. They don't want to share their data with anybody else on the cloud. So there's so many advantages that driving the inference to the edge. But cloud also has its own advantage as well. Like you have plenty of computing resource. It has large amount of memory bandwidth. All are important for inference. But we believe the best working model is a cloud edge collaboration model. So the training, in the foreseeable future, we still see the training doing in the cloud. And periodically, you will push the model down to the edge to do a better inference on the edge side. But with all this reason that we want to do the inference at the edge, but we have to solve the technical problem, right? So how do we get enough compute resource and memory capacity so that we can do the inference at the edge? And I would like to share with you today how MediaTek overcome these technology barriers so that we can deliver our AI solution on the edge device. I would like to introduce you MediaTek Helio P90 SoC. And it also incorporates an AI processor unit, which is consistent of VPU plus AI accelerators, and which you can deliver 1.1 teramax operations. And as Dino just mentioned, that MediaTek won the Vision Product Award of the Year for its AI technology. And I would like to invite you all to our booths right outside this conference hall and to take a look at what MediaTek's AI technology can do for you. Okay, eSearch AI benchmark is studied by created by the university at Germany. Independently studied the AI capability for the mobile phone application processors. And MediaTek Helio P90 received a high score from their study. And in the category of quantization and the floating point 16, and we outperform our peer by wide margin. Well, network quantization, we have heard this from many people. Network quantization and pruning are two important technologies that allow us to shrink our model size. If you do quantization from floating point 32 to integer A, we're able to reduce 75% of memory footprint, and also 90% of energy efficiency when you do inference. And network pruning is another important technology that DNN architecture have many redundant ways that helps the training model to converge. But those redundant ways does not adding any benefit to the inference process. So we are able to remove 20 to 40, to some of them even to up to 50% of a redundant way, which can directly shrink the memory footprint of an inference network. And if we apply both pruning and quantization to integer A, we can reduce the memory footprint by 80 to 90%, and energy to roughly 93%. This is one of the main technology that we're able to bring inference to the edge. But the key is, with all this memory reduction and the saving of energy, we still keep the inference accuracy within 1% of floating point 32 model. We can do it, a lot of applications just cannot sacrifice the accuracy just to do the inference. So this is a great technology. And I will talk about how we apply those technologies in our toolchain as well. Let me introduce you the features and architecture of our AI accelerators. Okay, the single AI accelerator, we abbreviate for AIA, can deliver 800 gigamag per second of integer A performance. And if you want to double your performance, you just instantiate 2 of this in your design. Then we can instantiate, get double the performance. And we also can do simultaneous execution of operation. Like for convolution, we can do simultaneous operation of convolution, activation, pooling on different block size. And we support different integer calculation, like integer A and 16, and also we support floating point 16 calculation as well. And in the AIA, we have two dual AXI bus, and we support 25 gigabyte of memory throughput, both for in and out of the AIA. And we have 3 techniques that we use to reduce the bandwidth for the inference technology. Is tile-based layer fusion. So instead of processing, taking the whole layer data, activation data in, we cut it to piece of the activation and bring those data in for processing. And also we fuse multiple instructions like convolution, activation, pooling into a single command. So those intermediate data does not need to leave the AI accelerator, can stay within. That will further reduce the memory bandwidth requirement. And sparsity compression is a very important technique for saving memory bandwidth. For certain network application, like LSTM, is memory bound. So if you can compress your memory, it will directly translate to increase the performance. And also, we support hardware symmetric and asymmetric quantization as well. And it can be done in per layer, or somebody call it per tensor, or it can be done in per channel manner. And this is all being done without any extra performance overhead. And with all these features, and MediaTek AIA can deliver 1 teraMAC per watts of power efficiency. That's almost 2x better than the VPU. Well, this is a high-level block diagram of AI architecture. And first of all, it has some programmability. The instruction or command will get loaded into the left-hand side of the command buffer. And the command buffer will issue instruction or signal to control the compute unit. At first, you will tell the convolution data loader to load the way and load the activation into the input buffers. Sometimes we talk about we compress our way in the DRAM. So when we bring it in, we will also decompress it before we put in the convolution buffer. And also, the format that the activation data stored in the DRAM is in NHWC, which channel will be in sequential address. But for convolution engine, as we know, we like to processing the XY direction first. So we need to convert the channel first addressing to an XY first addressing before it move into the convolution input buffer. And the convolution data dispatcher will dispatch the data to the convolution compute engine. Once the compute is done, we'll do quantization first before we store the data into the shared buffer, which is on the lower right-hand side. And the activation and element-wise engine, then pooling engine, will work off the shared buffer to perform its functions. Once the tiles computation for the tile is complete, you need to move the data out to the external memory. It can be an external tightly coupled memory, or if the size is too big, then you have to move directly to the DRAM. But in certain cases, we're able to forward those data into the convolution input buffer for the next layer of operation. So we call this deep layer fusions. This will further save the memory bandwidth. All right, so this is the diagram for the convolution engine. And we can support 1,024 integer A MAC per cycle, or 512 MAC for integer 16 cycle per cycle, or 256 floating point 16 per cycle. And the green box is our integer MAC unit. It can either perform 2 in-A operation or single in-16 operation. And the 14.16 design is separate from this from the picture. And also that we provide various computation mapping, we call it block size internally. For instance, for this example here, assuming that's an integer 16, we can process a 16-channel A high by 4. So if you multiply those together, that will be equal to the size of a MAC operation, which is 512 per cycle for integer 16. And we also have various formats, like for instance, you can do 32-channel and 4 by 4. We have many of those combinations. The reason we do that is we allow our compiler to pick the proper size to achieve highest MAC efficiency. That is important. And we talk about we're doing pipeline fashion design. We're able to do convolution, activation, pooling at the same time. And convolution can be working on block 1, and activation can work on block 2, and pooling can work on block 3. It's great. So we create pipeline type, so we have can provide large number of throughput for the compute unit. But this also creates a huge problem for the routing channel, because you need to provide so much data to the compute unit, and also so many compute units are firing at the same time, you have a DIDT issues. So that's something that we have to overcome in our design. So this is MediaTek's software toolchain called NeuroPilot and platform-aware ML kits. And this toolchain will ensure that deliver the highest performance for the user's network. And also, it can run the most efficiently on MediaTek hardware platform. Okay, so we talked about network reduction, network pooling, and network quantization will reduce the memory footprint, increase the efficiency. And our toolchain able to do network reduction and network quantization. And after it is done, the data is sent to the compiler, and also to do the network diffusion and decide the tile size and block size so it can run it more efficiently on our hardware. And those are called NeuroPilot. And NeuroPilot supports TensorFlow as well as Caffe and Onyx. And it is very tightly integrated with Android NN. But we add additional feature on top of it. So we're able to binding operation to hardware. If you know that your algorithm already run the best on certain hardware applications, so we can bypass the Android runtime, directly issue them to the hardware. So it will run it most efficiently. Okay, so our toolchain, the utility support network conversion and the quantization. And for our profiling, we able to collecting power number, performance number, and the memory usage and the throughput number. So this feedback will able to give the algorithm developers the feedback so they can adjust their network to run it more efficiently on MediaTek's platform. Of course, we also have a debugger for the software programmer to use as well. Well, MediaTek provides a very flexible hardware for the ever-changing AI algorithm. You can even run it on either CPU, GPU, or VPU, or AI, I just mentioned. And we improve the performance AI application by reducing memory bandwidth and increase the compute efficiency with our AI accelerator. And we also have our toolchain is highly integrated with the Android NN, and adding performance monitor to give a feedback to algorithm developer to optimize our AI algorithm to run on MediaTek's platform. And adding the AI capability, it enhances the end user experience, and also sometimes create many new applications which will be benefit to our customers. And the rapid advancement in the edge AI technology will drive more AI application to the edge, which is a win-win situation for our customer and the end user and the MediaTek. Okay. Last year, in fiscal year 2018, MediaTek spent $1.8 billion, almost $1.9 billion actually, on R&D. So it's our mission to be a change catalyst, empower our partners with a smart technology solution that will inspire users to connect with the next billion people. And we believe anyone can achieve something amazing, and we believe that they can do it every single day. And we call this idea everyday genius. And everything we do is dedicated to make that possible. Thank you.
So if you have a question, please step up to the mic.
I saw those engines outside of convolution engine. You have the pooling and bilinear engine and the element-wise add engine.
That's correct.
Now, what if you have some other stuff? Where is that going to go?
Okay. So we try to put as much functionality in, but you can never be, we want to be future-proof. That's what do you mean?
Right, because, I mean, you know, like, obviously the bilinear is coming from LSTM kind of stuff where,
That's correct.
and pooling we all know, and then, but, I mean, even for activation, for example, somebody changes from ReLU to leaky ReLU or CeLU or something. So you have to be, or even some other layer, which is not, which we don't know what that is.
That's correct. So for those layers that is not supported by the MediaTek AI accelerator,
Yeah.
actually we're able to pass in those layers to another compute unit, like a VPU or even CPU,
Okay.
or even GPU. And in our system architecture, which I didn't cover here, we introduce additional memory hierarchy to make the data transfer much more efficiently.
Got it.
Yeah.
Got it.
So we're able to do that by passing those intermediate layer to other compute unit to perform those layers that for those operations that is not supported by the MediaTek AI.
Right, but just the last question. So do they actually have to go back to system memory and come back?
No,
or?
no, that would be too power hungry, right?
Right.
So that's why I say we introduce the internal memory, layer memory to do the data transfer.
I see. Okay, thank you.
You're welcome.
Any other questions? All right, thank you, Bing.
Thank you.
Very great presentation. Thank you.